This talk is on the adaptive step towards the multiphase conjecture, and this is based off of joint work with Omri Weinstein. In dynamic data structure, we have an online sequence of update and query operations, and we need to cheaply maintain this sequence of operations by accessing our memory as little as possible. For example, consider undirected graph connectivity. We want to maintain an undirected graph G under insertion and deletion of edges while supporting reachability queries, that is, whether or not S and T are connected or not. So you're given a set of nodes, you're allowed to update the edges, and given S and T, you must be able to whether S and T are connected or not. Now, there are two possible data structures. One is to simply record all updates as in adjacency matrix, and for any given query, just run BFS. This would result in one update time and n query time. Now, for undirected graph, one could do something smarter. You could maintain connected components as in balanced tree. This would result in logarithmic update time and logarithmic query time. Unfortunately, we cannot do something smarter for directed graph. Now, in dynamic data structure, we want to study the optimal trade-off between update and query time. Now, towards proving the lower bound, we first need to define the formal model. The formal model, in fact, the only known one for showing unconditional lower bound for data structure is cell probe model. Here, data is arranged as a sequence of cells, each of size W, and usually W is of logarithmic. And here we only measure the query complexity of solving a given query or resolving a given update. All the computations are given for free. So in the context of dynamic data structure, for each update, you're allowed to probe TU cells. For each query, you're allowed to probe TQ cells. So for update 1, you update the query, the cell as 119. For update 2, you're allowed to update the cell as jump to 112 and update the previous content to 83. And for any given query, you have to be able to answer query 3 after TQ probes into the given memory cells. Now we emphasize that this is an unconditional lower bound as it applies to any imaginable data structure. And it is a purely information theoretic lower bound. The goal here is to prove a bound on max TU and TQ. Unfortunately, this abstraction of cell probe model comes at a price, making it notoriously difficult to obtain lower bounds. And it is also noteworthy that the conditional lower bounds is a different story. While it's been fruitful for conditional lower bounds for the past few decades, in the past 3 decades or so, there was a very slow progress on unconditional lower bound frontier. Friedman and Sachs first proved almost logarithmic lower bound for a large class of natural dynamic problems. And Petrascu and Demain showed the first logarithmic lower bounds for dynamic connectivity, which essentially shows that the previous example that he had is tight. And only recently, we could show something super logarithmic, in fact, log square. Petrascu wanted to prove a polynomial lower bound. in an attempt to circumvent this limitation of techniques, Petroscu proposed the following online set disjointness problem as a candidate. In phase one, you're given k sets and you are allowed to pre-process them. And in phase two, a set T is revealed and the data structure updates using NTU time. And finally, in phase three, an index is revealed and the data structure must answer whether SI and T are disjoint or not in TQ's time. Pictorially, consider the following sequence of updates and query. From given SIs, one first pre-process on the memory. Given T, we're allowed to update. And then given index I, one must be able to answer whether SI and T are disjoint or not after TQ probes into the memory. Then the conjecture is that I max of TU and TQ must be at least n's of C for some small constant C. Petroscu then showed that resolving multi-phase conjecture would have major implications on many interesting dynamic data structure problems, such as dynamic reachability, matrix vector multiplication, range modes. They should all take polynomial time. But the progress has been slow on multiphase conjecture. We know conditional lower bounds for multiphase conjecture. The conjecture is true condition on three-sum hypothesis, that is no n to the 1.999 time algorithm exists for three-sum. But for unconditional lower bounds, we only know of non-adaptive update or query algorithm, but such class of algorithm is very restrictive. For full adaptive query, the known trade-off is merely constant update time than near linear lower bound. Therefore, we are very far from proving the full conjecture. In this work, we proved the theorem on the following restrictive query model. On phase one and phase two, we do not impose any restriction, but denote the updated cells as green cells. Then on query, we consider the following restriction. SI is given free of charge. You first read from white cells, then from the green cells. So the data structure has unbounded but layered adaptivity. You are only allowed one alternation between the layers. And surprisingly, this generalizes all known set intersection upper bounds. Also, there exists a square root n upper bound for semi-adaptive data structure. And we show that this is nearly tight, as any semi-adaptive data structure for multiphase must have square root n subgroups. Now, how do we even try to prove this theorem? So let's go to Petroscu's original work. Petroscu introduced the following number on forehead communication game as a potential attack route for multiphase conjecture. Here, Alice is given S1 through Sk and index I. Bob is given T and I. And they want to determine whether S and T Si and T are disjoint or not. But here's the twist to the game. Charlie gets to send the private advice to Bob, but Charlie doesn't know the index of the interesting subproblem. Then they proceed in the usual two-party communication. Petroscu then conjectured that short advice cannot help much in computing disjointness. And it is straightforward to see that number on forehead conjecture implies the multiphase conjecture, as number on forehead players can simulate the data structure. Now, what is the intuition behind this conjecture? The naive intuition is the following. If the advice is small, Charlie roughly provides little or 1 bits of information about Si. So since it is small, Ellis and Bob might as well ignore his advice and solve f of xy in standard two-party model. But it turns out that this intuition is misleading, as previous work by Chapat shows that advice can provide Ellis a lot of information about T. And as an example, consider F being the equality, while deterministic communication complexity of equality is N. Just with logarithmic advice, one can reduce the required communication to O sub 1. And in fact, even for disjointness, one can reduce the required communication to square root n, even though the randomized two-party communication complexity of disjointness is linear in n. And all these examples show that Charlie's advice is very useful when Si and T are correlated. Therefore, the hope was that can we hope to prove number on forehead conjecture under product distribution? That is, when Si and T are all independent. Nevertheless, we show that this direction might not be the best one, as number on forehead conjecture implies a major open problem in circuit lower bounds, which we elaborate on this further later. This also suggests that the number on forehead conjecture is probably stronger than is necessary to prove the multiphase conjecture. Instead of proving in full number on forehead model, we consider the following restriction. Consider the restriction where only Ellis's first message is allowed to depend on the whole sets. The subsequent message depend only on the given Si and the previous transcript. This better captures the data structure, as data structure can only adapt based on the read cells, not all written cells. For simplicity, this can be also viewed as an equivalent four-party number on forehead model, where we introduced an extra player Merlin who broadcasts the first message, then disappears. Then we show that any four-party protocol for multiphase game with little advice requires at least square root of n communication between Ellis and Bob. And this is again tied up to logarithmic factor, since our communication model generalizes previous work's upper bound. And then a lower bound on this restrictive number on forehead protocol implies a semi-adaptive lower bound. As a main technical ingredient, we prove the following extraction lemma. Suppose x and y are distributed from Bernoulli 1 over square root n. If there exists a too good to be true protocol for multiphase, then there exists a random process with low information and low correlation. Then one can show that such random process cannot exist. So the main challenge here is extracting a random process achieving low information and low correlation simultaneously. If either one of them is high, then one cannot deduce any contradiction. As a final remark, now why is Petrascu's number on forward conjecture not ideal for proving multiphase conjecture? We show that there is a connection between his number on forward conjecture to that of circuit complexity of computing linear operator, which is a very well studied problem on its own right. Consider the following problem of designing a circuit with few wires for computing a given linear operator. A counting argument shows that if one limits to linear gates, that is, gates compute linear functions themselves, then for a random Boolean linear operator, the trivial circuit is nearly optimal. But the question remains open if we remove such restriction on the gates. If we allow arbitrary gates, highest lower bound is only slightly superlinear. A major open question is whether we can show a polynomial lower bound for random A. We show that Petrascu's number on forward conjecture indeed implies a polynomial lower bound for circuits with arbitrary gates computing random linear operator. We show this via showing that a cheap circuit implies a too good to be true number on forward protocol. Alice is given a linear operator A, Bob is given X. Alice therefore can construct a proposed circuit computing linear operator A. Now Charlie, as his advice, sends contents of all high Fanning gate contents to Bob. Now with high Fanning gate contents known to Bob, Alice only needs to query few bits from Bob to compute AI times X. So the main message of our work is that data structures are weaker than general number on forward protocols. And since Petrascu's number on forward conjecture implies a circuit lower bound, it might not be the ideal way towards proving polynomial data structure lower bounds. Indeed, the open question is whether we can extract a low correlation and low information process from a general fully adaptive data structure. Thank you.